Imagine two chaotic systems completely unpredictable on their own that we force to move in perfect sync using only occasional low-cost data updates instead of a continuous signal. That's exactly what this paper solves. This is the field of chaotic Lur'e systems, a class of nonlinear systems that show up in secure communications, cardiac rhythm models, and chaos-based devices. The goal is synchronization, making a slave system copy the exact trajectory of a master system, even though both are chaotic. The catch is that in real hardware, you can't send continuous control signals. You sample the system at discrete time instants and hold the control value you can send in between. This is called sample data control, and it's cheaper, more reliable, and easier to implement than continuous control. But it introduces a challenge. The longer the gap between samples, the harder it is to guarantee stability. So the central engineering question becomes, what is the longest sampling interval we can use while still guaranteeing synchronization, even in the presence of external disturbances? Existing methods already model this system as something called a linear parameter varying or LPV system, where the nonlinearity is captured by a smooth sliding between simpler linear models. But there is a subtlety. The controller only knows the parameter at the last sampling instant, not the true continuously changing parameters. Prior work either ignores this mismatch or handles it too conservatively, which forces the sampling period to be shorter than necessary. This paper's key idea is a two-layer polytopic LPV framework. The first layer captures the natural variation of the system's nonlinearity. The second layer treats the gap between the true parameters and the sampled measured parameters as an additional uncertainty layer. This gives a much more accurate and less conservative model of what's really happening between samples. On top of that, the authors designed a new time-dependent Lyapunov Krasovskii function. Think of it as a mathematical energy measure that must keep decreasing over time to prove the system settles down, combined with Wirtinger's inequality, a sharper mathematical tool for bounding how much a signal can change during a sampling gap. Together, these produce a set of linear matrix inequalities or LMIs, solvable conditions that, once satisfied, guarantee two things: exponential synchronization and a bounded effect of external disturbances, formalized through edge infinity performance. Instead of one fixed controller, they also use multiple controllers combined smoothly according to the system's current operating region, which further improves robustness. They test the system on dual circuit, a classic chaotic electronic system, with a sampling period of just over half a second. The synchronization error converges to zero in about 6 seconds, faster than comparable methods, which needed around 9 seconds. Even when they inject a pulse disturbance mid-simulation, the controller pulls the error back to zero. More importantly, they compare their maximum allowable sampling period against 9 existing methods from the literature, and their approach allows the longest sampling interval of all of them, meaning less communication overhead and lower computational costs in practice. In short, this work pushes sample data synchronization further toward what real hardware can actually use: longer sampling gaps, guaranteed stability, and built-in disturbance rejection, with direct implications for secure communication systems and other chaos-based technologies. From now on, we'll be summarizing one research paper like this in every video, so you can grasp the key ideas without spending hours reading the full paper. Stay with us.